All right, so today we're going to talk about logic and more about proofs, which is kind of apropos given the proofs that you'll be writing tomorrow for homework 1. So this lecture is going to have like a bunch of anecdotes and then like the actual computer science part in the middle and then some more anecdotes at the end. So we're going to kind of talk a little bit about, at the beginning, about what really is proof. And to discuss this point, I invented like a funny acronym. I don't know if it's like too silly to say out loud, but I want to talk for a minute about good old regular mathematics, or GORM. Okay, so what do I mean by this? Well, GORM is the math that like you've been doing for all your life. It's just good old normal mathematics. It's also what we use when we're talking in the lectures and when you're writing the homeworks. Okay, GORM proofs are written, as you know, in English or another natural human language. Okay, they're not written in any other way. This is how we do math. And in regular mathematics, every statement is true or false, and you try to prove the true ones, and you try to disprove the false ones. Okay, that's how things go. Now, what does it mean to prove things? So, I mean, this is what we tell you about your homeworks and when you're reading books and things. And in GORM, in good old mathematics, a proof is supposed to be rigorous and logical and convincing and complete and cover all the cases and should really convey to the reader why the statement is true and it cannot possibly be false. Now, in particular, this depends on a few things. It actually depends on the audience who you're writing for. I mean, with your homeworks, you're writing for the TAs, and you're trying to convince them that indeed you've correctly proved the statement you're supposed to prove. And it also depends on the assumed background of you and the readers, what you're allowed to take as obvious, what things need to be explained, and so forth. And that's how it goes in mathematics. And really, a proof, a good old regular math proof, is valid if it's accepted by mathematicians. Now that's a little bit weird, right? Maybe, or it might be a little unsettling because, it doesn't seem too formal, but that's how it goes in life, and that's okay. I mean, that's how good old regular mathematics works. That's how it worked for you in the past, and it's how it will work for you in the future. That said, you may want to, and mathematicians historically did want to, try to really exactly formalize what it means to be a valid proof. Okay, and to some extent, that's what we're going to talk about in this lecture. So let me start with some anecdotes. I want to talk about the four-color theorem. Well, originally it was called the four-color conjecture. Maybe you've heard of it before. It was made in some math journal in 1852, a long time ago, and it said that the conjecture was that every map of regions, like 2D map of regions, you can color the regions with 4 colors, at most 4 colors, so that you never have 2 adjacent regions with the same color. Okay? So this is an example of the United States where the regions are the states and they're colored with 4 colors here: yellow, green, blue, and purple and pink, such that indeed no 2 touching states have the same color. So you can do it with the map of the United States, and this person noticed that you can seemingly do it with every 2D map. Okay, we're actually going to talk a little bit more about this theorem several lectures from now when we talk about graph theory, but I'll just warm you up to it right now. Okay, so that was 1852, and it became a popular problem that nobody could solve, and it stayed that way for quite a long time, for 27 years, until 1879, when it was proved by the mathematician Kempe, who published his result in the American Journal of Math. Okay, then 1 year later, in 1880, a different person, Tate, found a different proof of the same theorem, the four-color theorem, published in this Scottish math journal. So that was great, and everybody was very satisfied with the four-color theorem at that point. Flash forward 10 years, and this person, Hewood, found a bug in Kempe's proof. He found a mistake. So of course, everybody's like, well, thank God we have this alternative proof by Tate. At least it's still true. But in fact, then 1 year later, another person, Peterson, found a bug in Tate's proof. And so it went back to being people did not know how to prove it. And I like to emphasize that these people were not like jokers. Like Kempe's proof was like, Kempe was like a well-known mathematician, and people were like very widely acclaimed, it was very widely acclaimed. People were very happy about Kempe's proof at the time. So that's a little nerve-wracking. And in fact, the story continues. So 76 years later, 75 years later, people still could not prove it. And no, sorry, I guess I overestimated. No, 78 years later, people continued to work on it without being able to solve it. A mathematician called Hish had been working on it, and he made some theoretical advances on trying to prove it, and he didn't prove it, but he did something interesting. He showed, through his work that you could reduce proving it to checking some finite number of cases. It doesn't look like the statement, in this statement it has to be true about every possible map of regions, which there are infinitely many, but somehow using math, he managed to reduce it in theory to a finite number of cases. But it was like way too many cases. He could not check them all. But it was good progress. Then 7 years later, these people, mathematicians / computer scientists, actually more like computer scientists, really, they're like, let's do this. We have computers now. So they wrote kind of computers in 76. They wrote this a massive amount of code. Actually, they did some theoretical work, too, to exactly enumerate what the cases were and how many there were. There were like about 2,000 cases. They wrote a massive amount of computer code to like solve all these cases. And after like 1,200 hours of computing, like it checked out. And they were like, we did it. We proved the four-color theorem. So that was very controversial at the time, from what I understand. And maybe people will ask themselves, wait a minute, is this really a proof? They accepted, let's say, Hish's part, where he reduced it to cases, and then they did some more mathematical work to kind of clarify what the cases were, and then they ran this computer code and said, well, it checked all the cases. So I want to ask you, what do you think? Is it a proof? Take a poll. Who thinks it's okay? Who thinks it's not okay? Oh, you're very one-sided. Okay, supposing you did not think it was okay, or supposing you really don't think it's okay, what are some objections you could have to this? Yes? That's true. That's a very good point. I mean, you said that one of the criteria for a proof is that basically the community of mathematicians accepted it, and that was not the case at the time. So actually, I don't know. They didn't take a poll back then, so I can't be sure. But there's certainly controversy. Yes?
There was a bug in the original proof. There could have just been a bug in the code that they wrote.
Yeah, definitely. There could have been a bug in the code that they wrote. I'm actually not sure historically if they published the code or not. I'm not sure. Yeah?
It's not written in English.
Yeah, part of that is it's not written in English. In particular, like a human could not duplicate the checking of the cases. Any other suggestions? Yeah?
The computer could be wrong.
Yeah, the computer could, for example, the hardware could be wrong. It could have been like a flaw in the hardware they used when they were running the checking. Any other suggestions? Oh, that's it? And more like even philosophical suggestions? Yeah?
What does it mean to have a computer tell us something about
Well, kind of, yeah. Yeah. Okay, so here are some things that I thought or people thought, and we said a lot of the same things, like a human wouldn't be able to duplicate this. Maybe the code had a bug. Maybe there's a bug in the hardware. This is a bit of a philosophical one. One reason we want to prove things is not just to be convinced that they're true, but also to try to understand why they're true, And just because a computer checked all these thousands of cases, mathematicians are pretty unsatisfied because they didn't get any insight really out of why it was true. Well, that's how it was for a while, and things stayed this way for a while, and it seems like most people came around to agree, like you folks did, that after a while people were like, okay, fine, we accept that this is a proof. This is the way it is. And so now, indeed, maybe it is a proof because, most people more or less accept that Apple and Haken proved it. Actually, I have more to say about this, though. Can even continue. So actually, when they were doing their work, they were classifying kind of the cases by hand so that they could figure out what computer code to run. And they first did a classification, and then they were checking it, and they found mistakes in their own classification. And they called them type 1, type 2, type 3 bugs. And they found that the type 1 ones they could fix in a few minutes, and the type 3 ones they could fix in a few days. I don't know what the situation was with the type 2 ones. So anyway, 4 years later, this person in Germany, for his master's thesis, he went through their code or their analysis of the cases, and he found like 14 different bugs in it. And they corrected them. So I mean, indeed, they corrected them according to this. And eventually, they published a book in 1989 where they like really made the math part like super clear. And nobody has found a bug in that. So okay, this makes us feel a little bit better about the proof, although it's still kind of a big pain. There's one more thing I can add. In 97, there's kind of a simpler computer proof where like the case analysis setup was simpler and the code was not as much. That was developed by these 4 people. So, partly because of these 2 things, people are now pretty satisfied with the 4-color theorem being proven. Actually, to the end of the lecture, we'll see even one more further fact that sort of bolsters the idea that, okay, we really did prove this 4-color theorem. Okay, I still want to tell a few more anecdotes on the subject of what does it prove and what does it mean to prove something and so forth. This is a fact or a bunch of facts about a theorem in math called the classification of finite simple groups. I'm not going to say what it is, but there's a subject called group theory, which is about some kind of algebraic structures called groups. And like the simple groups are kind of like the prime numbers of groups from which all other groups are built. And mathematicians wanted to find them all. Okay, that's what the theorem was about, or the problem was about. It actually even has some relevance for computer science. The fastest algorithm for graph isomorphism, if you know what that is faster if you know this theorem. Anyway, so the theorem is the form every simple group is one of these things. There's like a bunch of families and 26 extra finite simple groups. Okay, so people started working on this even in the late 19th century, and they worked on it and made progress and wrote more papers about trying to prove this and so forth. And it went on for a really long time, and like hundreds of papers got written contributing to trying to prove this that were like tens of thousands of pages when put together. And then people kind of started to lose interest a little bit. I mean, the people that like worked in this area were like really into it, and they're still writing these like hundreds of papers. But other people were like, man, that project is still going on. Like, I can't believe it. So then in like 1983, people were very happy because one of the experts, this guy Gorenstein, announced, we did it. Like, that last paper finished it. We have now proven the theorem. So people were, again, they were kind of happy that he proved it. But for most mathematicians, it's kind of like they were taking his word for it because nobody could really read, except for the super experts, could really read like 20,000 pages to verify that this theorem was true. And in fact, actually, there's like kind of a devious aspect to this story. From what I understand, this is kind of a bit like gossip, but apparently at the time, these experts actually knew it wasn't quite finished. But they were kind of worried that everybody had sort of stopped caring, and they kind of more or less knew that they could do it, so they were like, okay, we did it, to kind of get like some celebration and like interest going again. But they kept actually working to really finally finish it, and like in 2004, apparently now it's really, really finished. Like, they finished a 1,200 paper, and this time they were like, okay, honestly, this time we did finish the proof. So this theorem is also a bit controversial. People more or less accept it because there are enough experts who are pretty credible that say, okay, we really did it. They can answer questions for you if you like. Still, people kind of prefer not to use this theorem as part of another proof unless they really have to. And this is a real concern too. There's not that many experts, okay? So they're really worried that maybe they'll just all die before really it's collated properly. Like 5 years ago, I spent some time in this forested area called Princeton, and my older son went to a daycare there, and there's like another mom who had a kid in the same class named Ina, and a nice person. It transpired that I found out as the semester went on that she was a mathematician, and she was kind of famous. Indeed, she worked in this area. Indeed, she was more or less regarded as the youngest person that kind of more or less understood the whole proof. So this is a measure of the state of affairs. Now, they are planning a 13-volume series of books to totally like wrap it up and do it clearly and carefully so that hopefully everybody can read it and it'll be recorded for posterity. So far, they've completed 0 of these books. But they are working on it. I got a few more anecdotes. Probably the most famous theorem in math from the last century was Fermat's last theorem. It was mentioned even in Anul's first lecture. It's proven in '93 by Wiles, but it's less known that he announced his proof, and then actually a fairly big bug was found in it. And he corrected it later with the assistance of this guy, Richard Taylor. And even fixing that bug took like a 100-page paper. This one I would say, though, lots of experts understand this. Like many, it's not too long, the proof. This one is, very solid. People are very satisfied with this proof, albeit, it had a bug there for a year. This last anecdote I like too. There's a very simple geometric problem about shapes in n-dimensional space called the Boussemond-Petit conjecture. I could say what it is if I had 5 more minutes, but for a while it was known in every dimension. The answer was known for it in every dimension except for 4. And in '94, this guy Jung finally proved what the answer was. He proved that it's true in n equals 4 dimensions. And he published in this journal, Annals of Mathematics, which is the most prestigious journal in mathematics. You may guess from all these anecdotes that indeed there was a bug in his proof. It was pointed out by somebody else. So people started working on fixing it. And actually, this guy himself kind of fixed the bug ultimately. And it turned out he was exactly wrong. The n equals 4 case was false. And he published in the same journal. So it's pretty awesome that in this journal, like in '94 they had like theorem X, and then in '99 they have theorem negation of X. Okay, so I tell all these anecdotes partly for fun and partly to illustrate that proof is a slippery concept and it can sometimes fool the experts. I will say though that there are no such slippery things on the homework. Your TAs will be able to correctly verify whether or not you have proved the statement or not. But it illustrates the point that formalizing proof takes some care and it's worth it. Okay, so because of such incidents, many mathematicians became interested in, really formalizing these Gorm proofs, these good old regular mathematics, English language proofs. This even dates back to like 2,300 years ago to Euclid, as you may know, who was interested in doing this for the subject of geometry and also a little bit number theory. And it was pretty cool. He really invented the idea practically of starting from clearly stated axioms and making rigorous logical deductions based on these axioms to try to prove things. Now, it wasn't perfect. It was 2,300 years ago, so it wasn't ideal. He made some mistakes. For example, he assumed that if you have a circle and you put an infinite line through the center of a circle, that the line touches the circle. That's actually true, but it didn't actually follow from the axioms he wrote down. But still, he did a pretty good job of, developing rigorous proof. So people were kind of more or less rigorous for a while, and then this issue of really trying to get perfect rigor and maybe formalizing proofs really started to take off in the late 18th century. And as we'll see a little bit, it sort of culminated in the understanding that you really can, if you want, exactly logically formalize all the proofs that are normally written in good old regular mathematics, using deductive systems, which we talked about last time, and first-order logic, which is something we'll talk about this time. Just a few words on this. We'll talk about it a bit more later. Maybe the biggest heroes here were these two mathematicians. He's kind of a philosopher too, Russell and Whitehead. They kind of started a project to do this, where they're like, we're going to formalize all of math, just right from axioms, purely logical. They started writing these 3 really long books in 1912. They did it for 10 years, and they were kind of successful. Starting just from axioms of set theory, they went on and developed a bunch of mathematics purely rigorously with logic. But it's very exhausting. For example, they proved 1 + 1 = 2 on page 379. I actually don't know why it took that long. I guess they spent a long time on set theory before they got to numbers, because even if you start from the very beginning, getting to 1 + 1 = 2 is not that hard, but it's a pain. It's very much a pain, as we'll see, to really completely rigorously formalize all proofs. But it was good for mathematics because people kind of were after they worked on it for 10 years and with all these 3 thick books, they were like, okay, we could do it if we really wanted to. But, mathematicians don't really want to. I mean, as you know, they kind of went back to writing, math proofs in English language and stuff, just regular proofs. But they're at least happy that you could do this if you really wanted to. Actually, we'll talk about this a little bit more. The situation has changed a little these days. We'll talk about it a bit more at the end of the lecture. Okay, so now I want to get into the math part of the lecture. And we're going to talk about the main tool that's used to formalize proofs in mathematics, which is first-order logic. So first-order logic, or sometimes FOL, is an extension. It's an add-on to the propositional logic that we studied last time. Okay, so first-order logic, in a nutshell, it's propositional logic, the stuff that the quiz was about, plus, for all there exists, those things, equal sign, and three things which I'll talk more about: constants, relations, and functions. One very important thing to say is this also has variables. But in propositional logic, variables stood for things that could be true or false. Okay, their values were true or false. That's not the case in first-order logic. In first-order logic, a variable x stands for an object, some kind of mathematical object. Or if you're doing just non-mathematical logic, it stands for some object in the world. Okay, so yeah.
Can we just consider equals as a function?
The question is, can we consider equals as a function? Yeah, sometimes in first-order logic, they don't use the equal sign because you can formalize it without. You can get rid of it if you want. It's a bit nicer and easier to use equals, so we're going to allow ourselves equals, but it is sort of up to you. I'm going to do it by examples. So just like in propositional logic, usually the examples, they start by giving some English language sentences, and then they show how you would translate it into first-order logic. So let's start with this sentence. Alex is smarter than everyone. Is there anybody in this class named Alex? Yeah, you guys are going to get a kick out of it. No, actually, I just wanted a name that started with A and was kind of gender neutral. Okay, so this would be actually a naive way to formalize this sentence. And I do this slide not so much for the part about going from English language to sentences in first-order logic, because, I don't know, that's a problem of interpreting English, but just to give some examples of first-order logic sentences. Okay, so this is for all x is smarter, a comma x. So kind of what does this mean? Here x, as I said before, stands for an object in this, which is a person in this example. So this is saying for all people. A, I put it in boldface here. A is a constant name. It stands for a particular object. In this case, Alex. Actually, there are many Alexes here. So last time I taught this, there was exactly one Alex in the class, so it was perfect. All right, and this is a relation name. And usually, I personally write my relation names that start with the word is, but you don't have to. It stands for a particular relation. And I hope you remember what a relation is. A relation is something that maps objects to true or false. That's what a relation is. It maps objects, in this case, a pair of objects, to either true or false. Okay, I'm kind of explaining it by example here. Now, if you think about this, you might say the person that formalized this sentence didn't do such a great job because theoretically, x could be A, right? And it's you're saying, oh, Alex is smarter than Alex, which maybe doesn't make sense. So if you were more sophisticated, you might have think about it more like this. Alex is smarter than everyone else. Okay, and that's what this sentence is kind of saying. For all people, this is saying if x is not Alex, then Alex is smarter than x. Okay, and I give this example just to show more things. Here we have equality, and equality is equality of two objects. And we have the old stuff from propositional logic, and or, and not, and implies. Okay, so now I've shown you a bunch of the pieces. I think maybe you've seen this stuff before, so I hope it's not very new. So here's another sentence that will help us tell what functions are. That's the last thing I didn't mention, functions. So I wanted a concept that started with F for function. So here's a sentence, Alex's father is smarter than everyone else's father. You might specify it like this. For all x, if x is not Alex, then, see this is the father of Alex, and this is the father of x. We say that this person is smarter than this person. So what is the difference between a function and a relation? A relation maps objects to true or false. A function maps objects to other objects. Yeah. Okay, so this is the function name father, which stands for a function which maps objects to objects. Okay, so I've kind of told you all the pieces of this first order logic stuff. Any questions so far? Yes?
So we don't use the definition of a relation as a set of satisfied objects.
Yeah, the question was whether a relation, you might think of it defined as a set of objects or a subset of all the objects, or in this case, a subset of pairs of objects. It's kind of the same concept. I mean, a relation, you can think of it as a subset of the objects, and those are the objects for which the relation is true. It's the same concept, really. Okay. If you think of a relation as a set, then in my conception, where a relation maps objects to true or false, it maps it to true if and only if it's in the subset that is the relation. Yeah?
Then we run into a problem of whether deciding whether something is in the set or not.
Well, I'll talk about this in a second. The question is about deciding, I guess, whether the relation holds or not. So let me talk about that in a minute, and we'll come back to it. Yeah?
What kind of notation do we use for defining functions and relations?
Yeah, the question is what kind of notation do we use for defining functions and relations? Usually the best way is to explain what it is in words. But if, using formulas helps you, then you can also use formulas. There's actually a few, I don't want to dwell on this point, but there's still a little bit of a problem here of actually going between this sentence and this sentence. This is, I guess, a different question. Oh, yeah, that's exactly it. Maybe this is what you're going to say. I mean, what if X is Alex's sibling? Then, yeah, if Alex has siblings, then maybe this is not quite the same thing, because somebody could be different from Alex but have the same father as Alex. But in any case, as I said, I don't want to dwell on the going from English sentences to the formulas that much. I'll mostly stick with the formulas. But this is a good point. Okay, so let me be a little bit more formal about what goes on in first order logic. So one ingredient in first order logic, before you start to do it, in propositional logic, usually the first thing you say is, okay, these are my variable names, like x, y, and z, or whatever. In first order logic, you have to sort of start by saying, this is my vocabulary. Okay, and vocabulary has three components: a collection of constant names, a collection of function names, and a collection of relation names. Okay, and you'll say which are which. I'm going to give some more examples to clear it up, but this is kind of a confusing point. So on the previous slide, we had this vocabulary. There was one constant name, A, one function name, father, and one relation name, is smarter. And so far, vocabulary is just like, these are just kind of strings. They're syntactic objects. We didn't really say yet that this thing really means the father of the person. It's just a name. Of course, we had the idea in our head that it was modeling the idea that it was the father of the person, but so far it's just a name. Here's another example of a vocabulary. I just kind of made it up semi-randomly. I could say, oh, my vocabulary has one constant name, A, two function names, next, and combine. These little dots and commas show how many arguments it takes. So this is a function that takes one object and outputs another object. This is a function that takes two objects and outputs another object. Okay, so functions always they can take more than one object. They always output one object. And maybe one relation name, again, with two inputs and outputting true or false. Okay, once you decide on your vocabulary, then there's the notion of like having a well-formed sentence. And again, we could define this like we did last time with the deductive system, but I'm going to try to skip that part because I hope you'll kind of know what sentences are legal. Like these are legal sentences, It just means that all the connectives are in the right place and like you're only using the vocabulary and the parentheses are in the right place and so forth. Okay, so this is like saying for all x and for all y, if it's true that, is prior of x, okay, I'm not going to read it, but combine of a and y, it implies that next of x always equals y. It's a legal looking sentence at least. Okay. So now that we kind of know what are the syntactically legal objects, we're going to start talking about truth. And you're going to kind of see in the next few slides kind of rhyme with the slides from Thursday. I mean, it follows the same development as propositional logic. Okay, so let's take a sentence written in this vocabulary. There exists an x such that next of x, this is a function, equals combine of a and a. This is a function applied to the same constant twice. So, is this sentence true? Anybody know the answer? It's the same answer as on Thursday. Yes, this is a trick question that does not make sense. Just like before, a sentence by itself is not true or false. Whether or not it's true or false depends on the interpretation of the vocabulary. What these things, next and combine and a, means. Just like in propositional logic, a sentence is not true or false until you say whether the variables are true or false. Now, interpretation is a technical term. It's like a technical thing we'll define. Informally, an interpretation says what the objects are and what the vocabulary items stand for. So more formally, an interpretation has, 4 parts. It's a non-empty set, which is where the objects come from. That's called the universe. Okay, so in the original examples with Alex and his father, that was the set of all people. But we're going to see more mathematical examples in the rest of the class. And this is kind of the tricky part. The interpretation also maps each constant name to a specific object in the universe, each relation name to an actual relation in the universe, and each function name to an actual function on the universe. Okay, so for example, in the interpretation we had in mind back with Alex and his father, that interpretation mapped the symbol A to the actual person Alex. And it mapped, the relation name is smarter to the actual, if this even makes sense in real life, which I guess it doesn't, but the actual relation, whether or not this person is smarter than that person. Okay, so this is kind of a confusing part, so I want to give some examples that I hope will clarify it. Any questions before we get to the examples? Usually when you're doing first order logic, you have an interpretation in mind. You have something you're trying to reason about, do proofs about. You invent a vocabulary that's about what you're trying to reason about, and you have an interpretation in mind. So let's stick with this sentence, and I'll tell you one possible interpretation. So I have to say the universe, and for this, this weirdo example, the universe is going to be all strings of zeros and ones. So that's what a variable will stand for, a string of zeros and ones. A will stand for this specific string, 1, 0, 0, 1. Next of x will stand for the function that sticks a 0 at the end of a string. Combine of x and y will stand for the function that concatenates 2 strings. And is prior equals true, this is a relation, if x is a prefix of y. Okay, so under this interpretation, now that I've given an interpretation, now we can ask, is this sentence true or false? Can somebody tell me? We're getting some votes for false. That person way back there, do you have your hand up? You want to say why?
False.
Yeah, why?
Because next of x creates a string which ends in 0.
Yeah, next of x creates a string that ends in 0. Yeah, but combine a comma a gives you the string 1, 0, 0, 1, 1, 0, 0, 1, which ends in 1. So you couldn't have an x such that next of x equals combine a. Okay, so this interpretation makes this sentence false. Just like sometimes in propositional logic you have a formula, and then for some truth assignment it's false. But here's a totally different interpretation, same sentence. Here the universe is going to be all the integers. A, I'm going to say, stands for 0. Next of x stands for x plus 1. Combine of x, y stands for x plus y. And is prior xy is true if x is less than y. So for this interpretation, is it true or false? Somebody want to put up their hand and say why it's true or false and what it is? Okay?
This universe integers, they're looking for something which is successor
Okay, so yeah, so it's true. The sentence is basically saying that there's some number whose successor, for which x plus 1 is equal to a plus a, which is 0. And yeah, there is such a number, -1. Okay? So with this interpretation, the sentence is true. Here's one more example. It's almost the same interpretation, but now the universe is the natural numbers. Is it true or false now? Yeah, I'm getting some votes. It's false now because, the only x that could work here is -1, but that's not in the universe anymore. That's no longer a valid object. Okay, so and this interpretation, it's false again. Yeah. Oh, the statement was A is not in the natural numbers either. Yeah, it depends what you mean by the natural numbers. I prefer, and we prefer in this class, that the natural numbers include 0. It's a convention that's up to you, but I'll say now, in 251, the natural numbers will include 0. Okay, but that's a good point. That's a reasonable point. Okay. So next thing we want to talk about is the same concept from last time in propositional logic, satisfiability and tautology. We're going to have basically the same definitions. So in interpretation I, we saw 3 interpretations before, satisfies a particular sentence S if it makes it true. And we say that S is satisfiable if there isn't an interpretation that makes it true. And it's unsatisfiable if there isn't an interpretation that makes it true, or every interpretation makes it false. And the last one is S is a tautology if every interpretation makes it true. Okay, so again, just as before, every sentence, once you fix a vocabulary, it's either unsatisfiable or it's satisfiable. And if it's satisfiable, it might also be a tautology. So let me give some simple examples. An unsatisfiable sentence would be, there exists x such that next of x equals next of x is false. Next of x does not equal next of x. Well, that's unsatisfiable, right? I mean, it doesn't matter what the interpretation are, what the mathematical objects of the universe are, what next means. I mean, next of x equals next of x. So this is unsatisfiable. Yep.
Does next have to be deterministic?
The question is, does next have to be deterministic? Yes. A function, as normally understood, is a deterministic mapping from objects to objects. It's a reasonable question, though. Okay. An example of a satisfiable but not tautological sentence is this one we studied before, right? And we saw that there were some interpretations that made it true and some that made it false. So it's satisfiable because there's at least one satisfying interpretation, but not a tautology because there's at least one falsifying interpretation. An example of a tautology is, this one's a bit subtle. It's an implication. If for all x, x equals a, then next of a equals a. And this one is true no matter what next means, and no matter what a stands for, and no matter what the objects are, because, well, I mean, it sounds a bit tautological, but I mean, if everything is equal to a in your universe, then in particular, whatever next of a is, it's also an object, so it also equals a. Okay. Any questions so far? Yeah.
So, when you're proving something's unsatisfiable, at what point will you actually have to prove that elements exist? So, in this example, we assume that, there exists an x. So, would it be fair to say there exists 2 x's or 3 x's, etc.?
Well, here, if you're showing something as, this sentence is unsatisfiable, this one says there exists an x such that blah, blah, blah. So to show that it's unsatisfiable, you would have to show that there's always no such x. But I understand to some extent your question. There's a very minor technical point. I slipped it past you, but, well, let me not rewind the slides. But this is a minor technical point. We always assume the universe has to be non-empty. So, because then it's a little bit annoying. You can have a sentence that's like, there exists x such that blah, blah, blah. Like, there exists x such that x equals x. That for us is a tautology. And it relies on the super technical point that we always assume the universe has at least one object. But, so it's a good point. I don't want to get too stressed about it, though. Yeah. OK. So just to remind you, a tautology is something that's sort of automatically true for purely logical reasons. It doesn't matter what the state of the mathematical world is or what the objects are or anything. It's just always got to be true. And unsatisfiable is also something that's its truth or falsity only depends on logic, not on what the objects mean. And for satisfiable but not a tautology, it really depends, true or false, on what the interpretation is. So here's a sentence, and I want to reason about whether it's satisfiable, unsatisfiable, a tautology, what have you. So suppose I ask you, show that this is satisfiable. Well, don't even look at the sentence for a second. What is the task? You have to give an interpretation, which means you have to say what the objects are going to be and what all the constant names and, well, there's actually here only one function name, what it stands for, what actual function it is, and show that that interpretation makes this sentence true. OK, that's what you would have to do to show it's satisfiable. So let me do that. Here's an interpretation. There's many, many ways to solve this problem, as we'll see. But here's one. It's a simple one. I'll say the universe is all the integers, and next of y means y plus 1. So now let me prove to you that under this interpretation, this sentence is true. So if you look at this sentence, it's overall an implication, right? It's overall this piece implies that piece. And let's look at what the hypothesis part means. There exists y such that for all x, x equals next of y, which in our interpretation means there's some integer y such that every integer equals y plus 1. Well, is that true or false? Yeah, it's false, right? There's no integer such that y such that every integer equals y plus 1. So under our interpretation, this piece is false. And now we're pretty much home free. In fact, we don't even have to worry about whether this piece is true under our interpretation or not, right? Because false implies anything is overall true. So under this interpretation, the whole thing is true, and so the sentence is satisfiable. OK? I'll come to you then. Now actually, we might ask, is it a tautology? And this raises a kind of an interesting point. In propositional logic, if I ask you if something is tautology, if it's always true, you had kind of a few strategies maybe to try to prove it. You could maybe reason about it using equivalences. But sort of as a last resort, right, you could always just be like, well, I'll write down the whole truth table and just mechanically see if, like, under every assignment it becomes true. Okay, you could always do that. But in first order logic, things are harder. You can't do that because there's no truth table method, because to show that something is a tautology, you have to show it's true under all possible interpretations. That means every choice of universe and every choice of what the names in the vocabulary mean. And there's infinitely many possible universes. So seems tough. But sometimes you can do it using good old regular mathematics and good old regular reasoning. And in fact, in this case, you can do it. This one actually is a tautology. And can anybody tell me why? OK, I know you're working on it, so yeah?
So for every possible x, next y can only have one value. So if every possible x equals that value, there can only be one possible x. So our universe has to be of size 1. And if our universe is of size 1, then there's, for all w and for all z just means the only w equals the only z, which has to be true since there's only one object. So the second part is always true, so the implication is always true.
Yep.
If the first part is true. If the universe has more than one object, the first part is false, and the implication is true.
Yep, that's exactly right. Andy said it with a pretty loud voice, which is good. So you can check the tape later, but I'll quickly say, to show such a tautology, you have to say for every interpretation why this is true, even though you don't exactly know what it is. But if I is any interpretation, well, maybe it makes this part false. In that case, we're done, just like on the previous slide, because that would make the whole implication true. OK, maybe it makes this part true. But in that case, it's saying in your universe, there's some y such that everything equals next of y. So I mean, whatever next of y is, everything equals it. So in particular, that kind of means that actually there's only one thing in the universe. It would have to be that your universe is of size 1, everything is equal to each other. And that's exactly what this last part is really saying. For all w for all z, w equals z, that's saying that everything is equal to each other. So we managed to do it. We showed that no matter whatever the interpretation is, it makes the sentence true. Okay, so sometimes you can do it using good old regular mathematical reasoning. Okay, now actually it's kind of a shame that there's no truth table method. It's kind of great in propositional logic that, at the end of the day, if you really wanted to, you could just figure it out mechanically by just writing down the whole truth table. And you might wonder, maybe there is some kind of, maybe there's some kind of mechanical way you could check if a sentence is a tautology. That would be good. Yeah, so this gets at the whole program that was started in the early 20th century to try to formalize all of math. So these two people, Frege and Hilbert, had an idea for how you might try to check if something is a tautology. And they invented this idea, which is usually called Hilbert's system, which is a bit unfair because Frege also invented it. So we'll call it first-order logic deductive calculus. I'm not going to exactly define it, but I want to give you the idea. It's some kind of deductive system for generating tautologies in first-order logic. So I just want to give you a flavor of it. Again, I won't precisely define it, but if you open any serious textbook about logic and you go to chapter 1, it'll tell you some kind of deductive system, a first-order logic deductive calculus, that will have a bunch of initial tautologies and usually one deduction rule. Okay, and the initial tautologies are stuff that is always obviously a tautology. Like if you have any sentence A or not A is a tautology. Or if you have some relation is R applied to A implies there exists X such that is R of X. If you think about it for a brief amount of time, it's kind of clear that this is always true, no matter the interpretation. Okay, so I won't get into it, but they give you a bunch of tautologies and families of tautologies that are always, tautologies. And they also give you one deduction rule for generating new tautologies, which is usually this one. If A is a tautology, so it's always true, and A implies B is a tautology, so it's always true, regardless of the interpretation, then you're allowed to deduce B. And that makes sense, right? Then B would also always be true. It would be a tautology. Okay, so it's some kind of formal syntactic deductive systems that you can use to write down things that are tautologies and then start to crank out more tautologies. Yeah?
This doesn't necessarily generate all tautologies in the system, right?
Well, this is what we'll discuss in the next slide. Yeah?
Why can't you do something like and two tautologies or them? That would still be a tautology.
Yep. So yes, A and A. Well, if A is a tautology, then A and A is a tautology, right?
If A is a tautology and B is a tautology, A and B.
Yeah, so there's not one fixed first-order logic deductive calculus. Every textbook kind of has a slightly different one, and you may find one that includes that as a deduction rule. So one thing, about this idea that Frege and Hilbert had is that anything that's deducible in this first-order logic deductible calculus is a tautology. And it's kind of by design, right? They set up the whole system so that it would only make tautologies. But yeah, the other question is very interesting. Is every tautology for a given vocabulary deducible? That would be great. So there's a person who had something to say about this. It's an Austrian guy called Kurt Gödel. He thought about this question, and turns out the answer is yes. This is his famous Gödel's completeness theorem. He proved it in his PhD thesis in 1929. It's a pretty hard theorem. We're certainly not going to prove it, but it's true. So this is actually pretty awesome. He showed that once you write down, fix your vocabulary, then it's possible to get every single tautology just by cranking out more and more sentences with this first order logic deductive system. That's a pretty cool fact. So one way to kind of think about it or remember it is that if I have a sentence and it really is a tautology, there's a purely mechanical, formal, algorithmic way to check that it's a tautology. You could do a brute force search over all possible deductions in this first order logic deductive calculus. Yep?
Didn't Gödel come up with incompleteness that self-references as self-negates itself?
Yeah, Gödel had another theorem called incompleteness theorem. Two of them, actually. Number 1 and number 2, which we'll talk about in lecture 15. This is the completeness theorem, which is, those ones will actually prove. This one is pretty hard. We won't prove it. Those ones are not very hard to prove. Good question, though. OK. One more thing to define. It's sort of the same as in propositional logic. It's logical entailment. So, just asking whether a sentence is a tautology or not is sort of interesting. But usually you do a slightly different thing. You say, let's say I assume some sentences A1 through AM as axioms. And I want to know, is S a logical consequence of them? That's a more typical thing you use first order logic for. We'll see some examples in a second. But we're going to have the same definition as in propositional logic. We see that A1 through AM entail formula S if every interpretation which makes the axioms true also makes S true. Okay? In other words, if you assume that an interpretation satisfies all the axioms, if they entail S, it means the interpretation necessarily also satisfies S. So it's the same as tautologies in a way. It's the same as saying that A1 and up to AM implies S is always true for every interpretation. And using these notions, you can start to formalize mathematics, good old regular mathematics. And this is how it can go. You think of some universe you want to reason about, maybe geometry or arithmetic. You invent an appropriate vocabulary. You start with some axioms which are true under the interpretation you have in mind. And then you try to see what these axioms entail. And what's nice is by Gödel's theorem, that's equivalent to what you can deduce from them in this first order logic deductive calculus. I'll give you some examples. Historically, the first example that was tried to be like that was Euclidean geometry. This is just the basic sort of high school geometry of shapes in the R2, 2 dimensions. So Euclid tried to do this. These were his axioms. He had 5. Well, I guess they were written in Greek, but this was like to describe a circle with any center and radius. That does not look too good. So this is not really a proper formalization of Euclidean geometry. He tried. But this was the real hero here, Tarski, who did it exactly right in 1950s. This is like a heroic accomplishment. So I'm going to tell you his axioms and the interpretation he had in mind. His interpretation, the universe was points in the plane. And he said, this is my vocabulary. I don't need constants or function names. I'm going to have 2 relations, is between and is same length. And this one is supposed to mean that y is between the line segment xz. And this one is supposed to mean that this line segment from x1 to x2, these are points, remember, is the same length as the one from y1 to y2. And he wrote down some 11 axioms, the first, or some 4 of which I wrote here, which are, true. Like this one says, if you have 2 points, x and y is between x and x, then y equals x. It's true, right? So he wrote down these axioms, and then he started to reason about what you could deduce from them in this first order logic deductive calculus. Certainly anything you deduce based on these axioms is a true statement of geometry. And what was cool, he proved it using just regular mathematics, is that these 11 axioms are complete for Euclidean geometry, which means the other thing. Every true statement about geometry can be deduced from these axioms. For every true statement in Euclidean geometry S, these 11 axioms entail that statement. So you can deduce it using deductive calculus. So that was pretty awesome. In some sense, like, you kind of completely, 100% rigorously formalized high school geometry. Okay, here's another example that people worked on in the late 19th century, arithmetic of the natural numbers, 0, 1, 2, 3, 4. Okay, and we don't want to get into calculus or anything crazy. They were like, let's just talk about basic, number stuff. So the hero here was, this Italian person, Piano, who invented a vocabulary and axioms for arithmetic. Has one constant named 0 and 3 function names, successor, plus, and times. Successor is supposed to mean x plus 1. And plus and times mean, plus and times. And he had 7 axioms. There's enough space I could literally write them all down. These are called Piano's axioms. And some simple stuff that says no numbers, successor is 0. This says that if x plus 1 equals y plus 1, then x equals y. X plus 0 is 0. This basically implies that addition is associative. This one says x times 0 is 0. This one basically says that multiplication distributes over addition. And this one is induction. Actually, this is not just one axiom. It's a family of axioms. Okay? Again, you don't have to like study this. It will not be, you don't have to remember these, but it's for illustration purposes. So he wrote down this vocabulary, and he said, here's some axioms about number theory that you can get started. What can you formally prove from these axioms? Now here, we do not have this exact same situation like Tarski and geometry, but it's pretty close. So how complete are these axioms? This is not a formal answer, but it's an answer based on experience. 125 years of experience in math, they're pretty complete. Pretty much almost all true statements about arithmetic that you can formalize using his vocabulary can be deduced from them. So even complicated theorems like the prime number theorem, Fermat's last theorem, the theorem that every number is the sum of 4 squares, you can deduce them all these arithmetic theorems you can deduce from his 7 axioms. There's a few like intentionally designed, but not too crazy, arithmetical theorems that we know they're true, but you can't just get them from Piano's axioms. But this is a very rare case. They were like intentionally designed weirdo statements about natural numbers. So kind of the magic here is that he has such a simple set of axioms that you can use to prove almost everything. Yeah, for example, these sentences, it's not hard to prove them, but one step you need to do in the proof is say something like, for all sets of natural numbers, such and such happens. And you can't actually say for all sets in first order logic of natural numbers. You can just say for all numbers. Okay, but it's a pretty cool system. So that was a pretty successful story from the 19th century. And so right around the turn of the century, people were like, okay, let's get crazy. Let's figure out a system that will let us formalize all of math. So, in order to talk about all of math, not just you need to be able to talk about geometry and calculus and arithmetic and group theory. They needed kind of one language that could talk about all of those things. And they sort of decided on set theory. It's kind of hacky, but you can, it seems, express everything you want to talk about in math using set theory. So again, don't look at this very carefully, but if you only have sets, you can invent some definition of the natural numbers, and you can invent some definitions of ordered pairs, and you can define the integers from natural numbers and the rationals. And so they did all this stuff in the early 20th century. And it's very hacky. It's kind of like doing programming in some ancient language like COBOL, where you have pathetic data structures that are very annoying. And there's a modern approach called type theory, which is actually superior, but let me just stick with how they did it in the olden days. So then they're like, okay, let's do some nice vocabulary and axioms for set theory. And these were mainly invented by this person Zermelo. And one thing they liked about it was that it's very elegant, because it had no constants, no functions, and only one relation called is element of. Okay, here the universe was all the sets, and you just had this one relationship for element of. Okay, and there was 9 axioms, which I wrote 2 of them here. This one says if x and y are sets, then there's another set called the 2-element set containing x and y. So it's some simple stuff about sets. These axioms came to be known as ZFC. Some catchy thing, Z stands for Zermelo. So he invented some 9 axioms, and people tried to, use them to prove everything they could about sets and also about numbers and calculus and geometry and algebra. And we have a very similar outcome as with Peano's axioms for arithmetic. It's been around for 100 years, and it seems like it's amazingly complete. It seems that almost all true statements about, good old regular math could be defined and deduced just from these 9 axioms, ZFC. In particular, everything we were going to do in this entire class, you could, mathematicians agree, completely formalize using just this set theory axioms and this first order logic deductive calculus. Okay, so this is something about the logical foundations of mathematics, and people are pretty happy about this. This is what I just said. But it's super painful if you wanted to actually do it. And you'll notice that when a mathematician or a computer scientist writes a research paper, they don't write their proof starting from the axioms of set theory. They, at some point, went back to just writing it in English language. It's because it's super painful to do this by hand. But in the last 10 minutes, I'll tell you some anecdotes about this that have sort of more modern developments. So flash forward 100 years to now. Okay, this is a person who lived in the 16th and 17th century. His name was Lord Wacker von Wackenfels. It's not a joke, that's true. I probably said it very poorly. It's probably Lord Wacker, yeah, anyway. It's not really his story, it's more a story about Kepler. So in 1611, Wackenfels was Kepler's patron. Kepler is the famous astronomer. He gave his patron a New Year's present, which was like a math paper. And it had this conjecture. It said the densest way, suppose you had to pack identical spheres into space, how could you do it in the most efficient way, like where you left as little space left over as possible? There's kind of an obvious way to try it. It's to stack them in this familiar method that is used to stack oranges at the supermarket or cannonballs. It's kind of seems clear that it's the best, most efficient way to pack spheres. So he conjectured it, but he couldn't prove it. And it became a very famous problem called Kepler conjecture. Nobody could prove it for 375 years. Flash forward a really long time. This person, who works right over there, Tom Hales, he's a professor at Pitt, proved it in 2005, and it took a 120-page paper appearing in Annals of Mathematics, the most prestigious math journal. It was very awesome. I mean, this is essentially a 400-year-old problem. Well, actually, a bit like the four-color theorem, it took 120 pages of math plus computer code to solve 100,000 optimization problems, which took 2,000 hours of computer time. So he, again, somehow reduced it to checking a bunch of inequalities about real numbers and then got his computer to check those inequalities. So it was kind of like, the four-color theorem situation squared, or times 10. Yeah, it was even more complicated. They faced sort of the same dilemma. But actually, the Annals of Mathematics was very heroic. They got a team together of 20 referees. Usually, if you write a paper, there are 3 referees, so they got 20. They worked on it for 4 years, trying to check his work. Again, usually maybe 6 months is how long the referees might take, so they did 4 years. Some quit, some retired. One of them died. And in the end, they gave up. They published it, and they were like, we're 99% sure it's a proof, but we just couldn't, you're supposed to check things or duplicate things in science, right? And they're like, we couldn't do it. But Hales is a hero. I love this guy. I'm sad that I haven't met him, even though he works just a few blocks away. He was like, you know what? I'm going to code up a completely formal, axiomatic, deductive proof and check it by a computer. So he started this project to do it in 2004. For some reason, he called it Project FlySpec. And I followed its progress for a long time. And awesomely, he finished it in August. So he did it. It's pretty awesome. So let me talk a little bit more, in the last 6 minutes about what this means. So computer-assisted proof, it's an interesting topic. There's something called a proof assistant, which is a kind of software. Here are the names of some well-known proof assistants: Hall Light, Cock, Isabel, etc. This software does two things. One, it checks that a proof that's like encoded in this first-order logic deductive calculus is valid. And that's a very simple computer program because it doesn't have to know any math or anything. It just has to check that each line is either one of these initial object tautologies or that it syntactically follows from some previous lines by the one deduction rule. So it's really just like a very simple string checking program. Actually, as I said, I lied a little bit. The more modern method uses lambda calculus rather than first order logic, but it's the same principle. And also, these proof assistants help the user, the human mathematician, come up with these super long formal proofs. I mean, this is the main part. This is kind of a trivial programming exercise. And developing this kind of software is a very active area of CS theory research, particularly here at CMU. And it helps or it assists with this question that came up with the four-color theorem, like, is a proof valid? So suppose, like Hales did, you come up with like some giant formal proof, electronically coded, and this Hall Light program checks that it's a valid deduction. Can you trust it? Well, the good thing is you don't need to trust that the mathematician got the proof correct, in some sense, that the million lines are all valid deductions. You don't need to trust whatever crazy method the mathematician used to come up with that million lines. You just need to trust that this little string checking program that checks that each line is validly deduced from the previous line is correct. And this is some like 430 line piece of code that, many people have studied. So in a way, it almost makes you feel that proofs done in this way are like better verified than ones that appear in like math journals. So people have done this for various famous theorems, like fundamental theorem of calculus. Somebody coded up a complete correct deduction, and then Hall Light or some other program checked it. Fundamental theorem of algebra, prime number theorem that was led by a person in the philosophy department here at CMU, Jeremy Avogad. Gödel's incompleteness theorem, which we're going to prove in lecture 15. Hales sort of warmed up for his efforts by doing the Jordan curve theorem, which is a kind of a famous theorem in mathematics that seems simple but has a very tricky proof. Some other theorems. And the last three I'll mention are kind of like the most famous examples. They all took place within the last 5 years. This person, Gonthier, at Microsoft, gave a completely computer formalized proof of the four-color theorem. This took him many years. And so now, I think the four-color theorem is like the most well-verified theorem in all of mathematics, practically. Then Gonthier later did Fiat-Thompson theorem, which is kind of like the first 1% of the proof of that classification of finite simple groups. And then, as I mentioned, Hales, with a team of like 25 people, it was an open source project, actually, led by Hales. Just in August, proved this Kepler conjecture about packing spheres. Well, it's pretty cool stuff. So I find this area of research, I don't work on it, but I find it extremely interesting. And let me just end by showing you the proof of the four-color theorem. It really looks like this. And, I want to show you because it's connected to computer science. It really looks like code. These are actually, well, you can think of it like first-order logic. It's actually some lambda calculus plus a lot of syntactic sugar. But, this is what you input into this 430-line proof checker. It says that basically if you have a simple map, then it's colorable with 4 colors. Well, really, this is like the main function of the theorem. Like the first thing that gets studied. There's actually 60,000 more lines of code. But, well, you can look it up. It's also online. So that's what the proof looks like.
Have any computer-assisted proofs been disproven or found errors?
Have any computer-assisted proofs like they tried to formalize it and it turned out to be false,
like
or?
their code turned out to have a bug or anything, and it was accepted, and then
Do you mean the verifier or like the code that they applied it to?
sure.
I'm sure lots of times like somebody coded up a proof and like the verifier were like, no, you made a mistake. The verifiers, not usually, right? I mean, they're very simple pieces of code. Okay, I believe that you can pick up your quiz by first exiting the classroom and like going into that lobby over there. And we'll see you tomorrow for the homework.